My name is Georgia, and we are back on the second episode on the series of Blatter Radicals. Last time we had talked about the three aromatic sites of the Blatter Radicals, their stabilities, and their basic electronic and magnetic properties. We talked about how useful these radicals can be and how stable they are compared to chloride radicals. Now, the time has come to answer other, more pressing questions, like how they're made and what their synthetic mechanisms are. Before we continue any further, I need to warn you that the following video contains a lot of structures, mechanisms, and complex schemes. This video is not for the light-hearted. That being said, to those who remain, enjoy. There are three main routes to making Blatter radicals, depending on the different precursors used, which in turn depend on the substituents you want on your Blatter radical. None of these routes are perfect, as is usually the case. Some may use toxic reagents, have low yields, long routes, and in one way or another be unsustainable. Each synthetic route, however, opens up a whole new library of Blatter radicals with different electron distributions and reactivities. The reason for this is due to the varying tolerability of the intermediate species. In route 1, the classical route to Blatter radical synthesis is seen, with a ring closure taking place at position N1. There are two mechanistic pathways to get from 2A to Blatter radical 1. One would involve a single electron oxidation, generating an unpaired electron on N1, forming radical 2C, followed by cyclization and further one electron oxidation to yield radical 1. Alternatively, a 2 electron oxidation in situ to give 1,2,4-diazobutadiene 2B, followed by an electrocyclization and oxidation would give the same result. Various oxidants were tried out. Initially, excessive amounts of toxic and expensive mercury oxide or silver oxide were used most frequently for the final electrocyclization, but ultimately DBU in air with palladium catalyst was preferred. Now let's see what the mechanism behind the formation of Blatter radical 1 and route 1 is. The first part of route 1 indicates that three different products were formed, resulting in a low atomic economy. 2A must therefore be carefully isolated from a mixture of products of 2A, 3C, and 3D. Here, the yields of 2A and hence of Blatter radical 1 was highly dependent on the purity of 2A following its isolation through recrystallization. Alternatively, by combining chemicals 3E and 3F, we can limit the formation of byproducts and have a much preferred, cleaner pathway. Synthetic route 1 overall had moderate low yields, initially used toxic reagents before alternatives were found, and provided a means for making Blatter radicals with short route lengths. Moving on to route 2. The main differences between route 2 and route 1 is the oxidative site and the bond formed between the reactants. By forming the hydroxides 4A and cyclodehydrating to give radical 1, the formation of highly reactive intermediates like 2A are avoided. 4A can be made directly using hydroxides reacting with parafluoronitroaryl compounds, making this scheme ideal for alkyl analogues at R3. The mechanism for route 2 is different to route 1 and is as follows. The main advantage of route 2 over route 1 is twofold. It leads to the radical 1 via a very stable precursor 4A and a unimolecular cyclodehydration step. A stable intermediate leads to fewer side reactions, whilst a unimolecular dehydration has a faster rate of reaction compared to bimolecular reactions due to a smaller entropic penalty. Additionally, there is a range of substituents that can take the place of R1 and R3, giving flexibility to scheme 2, which would otherwise be difficult with route 1. That being said, the overall yields of both route 1 and route 2 are comparable, but the route length of 2 is longer than that of 1. This results in the process being less green. And now, considering the final general scheme, route 3. This route has a similar first step to route 2, with the main advantage being that post-cyclization substitution reveals a vast array of choices for different functional groups on N1 position. The mechanism is quickly laid out here. The importance of N1 substitutions is that we can effectively control the spin distribution and therefore electrical and intermolecular spin exchange interactions of the Blatter radicals. These additional choices for N1 substitutions are accompanied by higher yields of the reactions compared to schemes 1 and 2. Unfortunately, although scheme 3 has opened the door to various new substituents at N1, these are limited by low tolerance to functionalities that are compatible with alkyl or aryl lithium reagents. This table quickly summarizes some of the pros and cons of the synthetic routes shown. And that is all for today's episode of the Blatter Radicals. To those who survived until the end of this video, congratulations. If you were paying attention, you will now know more than is ever necessary about the general mechanisms for making Blatter radicals. You will know about the classical route 1, preferring to undergo condensation reactions of 3e and 3f to have a higher atom economy. You'll know about route 2 reactions of halonitro-arenes with hydrazines, followed by a dehydration, giving new possibilities for alkyl groups at R3. And finally, you will know about route 3 and its superiority in yield and substituent choices at N1. Ultimately, any of these routes can be used to create the Blatter radicals we want. However, depending on the substituents you want to include, some may be better than others. Until next time, with more Blatter radical chemistry.